Hello, I am Matis from the University of Tokyo, and I would like to present our submissions to the WAT shared task. We represented the team UTMRT, which is a clever abbreviation of our first names. Our team participated in the document-level business scene dialogue translation subtask, which involved translating a test set involving these 6 scenes: face-to-face, phone call, general chatting, meeting, training, and presentation. To train our models, we used the data provided by the shared task, which is the top row of the table, BSD20, amounting of 20,000 sentences from English and Japanese, Japanese to English. We also had a larger data set of the same business scene dialogue, about 80,000 sentences, and 2 other similar data sets with conversations, the AMI meeting corpus and the Onto Notes parallel corpus. And for larger, slightly out of domain datasets, we used the full WMT dataset, which also involved the JParaCrawl corpus, 17 million and 10 million, and a proprietary news dataset, which is document aligned and a little over 1 million parallel sentences. As for pre-processing of our datasets, we performed data filtering on all experiments involving the JParaCrawl, which is automatically crawled and aligned corpora from the internet, so there can be a lot of noise expected in that. We removed repeating parallel sentences, sentences where the source and target pairs are identical, sentences where more than half of the characters are outside of the scope of the language, for instance, Japanese into English, or too much English characters in the Japanese side. And we also removed sentences where the automatically identified language using a language identifier tool was different from the one that was expected. For pre-processing, we only use sentence piece for NMT with vocabularies of 3, 8, 16, and 32,000, depending on the dataset size for the training to the experiment. We only used tokenization on the Japanese side for evaluation, so that blue can be scored, and which requires spaces. For a few SMT experiments that we performed, we used Moses tokenization, true casing, and all the regular scripts that come with Moses. We experimented with training 3 main different types of models. For only the provided dataset, we figured that the old statistical machine translation approach may actually lead to better results because neural models tend to struggle with very small datasets. Of course, we trained normal transformer neural machine translation models, several types of those, and we also attempted experiments with involving previous context, since this is a document level machine translation task. For SMD models, we only tried one main configuration, which was using Moses, word alignment with FastAlign, 7-gram translation models, reordering models, language modeling with KNLM, and tuned using MERT. As for NMT models, we experimented with, first of all, using 2 different toolkits because each of them had different characteristics which the other one didn't, and which we required for some of the experiments. And we tried Sakai and Marion, and we tried 2 different sizes of the models, a base transformer of 6 layers and a small one with only 4 layers. With the Sakai models, we experimented with using previous context and domain tags, specifying which corpus or domain does the current sentence come from? And we experimented with averaging models for the highest scoring models. And for Marion, we only trained the base size of the transformer. The one feature why we chose some experiments with Marion was that it supports optimizer delay, which we set to 8 mostly, which basically means that the gradients are accumulated and updated more rarely, so that it can basically simulate larger batches and having larger GPU memory. We performed normal domain adaptation, which did not work as well in the Sockeye toolkit. And in the end, for the absolute best performance, we tried model ensembling. For our context-aware experiments, we trained the regular transformer models with the Sockeye and only modified the training data by adding the context sentence where it was available in front of the content sentence and with the beginning of sentence tag in the middle. And we also used source side factors to specify which token is a context part and which is the main sentence part. We had many intermediate results of our training. So in this table, the first rectangle is only using the provided 20,000 parallel sentence business scene dialog corpus. And as we see, the transformer base models significantly underperform the small ones. I guess they're too big for the little amount of data that there is. And in terms of the small models, we tried adding the context, and it seems that it only somewhat helps in terms of blue score for English into Japanese, but for Japanese into English, it seems that it gets lower every time. And in the lower parts of the table, we experimented with other configurations of the corpora and some model changes. The second big rectangle is using the same training data, but just changing from Sockeye to Marion, which we found that had different default parameters. And then by adding the optimizer delay of set to 8, we actually got a significant improvement. And then finally, just by tuning, we got a very huge jump in blue score as well. And this table shows all of the systems that we submitted to the shared task. Interestingly, at the very top, it seems that the SMT does actually perform very well and actually outperforms all of the other approaches from English into Japanese when using only the provided data of 20,000 sentences. But of course, when using additional data, NMT models gain significant traction. And in the end, it seems that we reached the very, very highest blue scores with not using context at all, but just adding as much of the data as we could find and tuning the models and assembling them. In this table, we can see the human evaluation results. The table is ordered by the human score from 0 to 5, and all of our submissions are in the bold font. At the very top, we can see that the highest scoring ones were the same that the humans preferred most, which did not use context but just had most data used and tuned and ensembled. And in the very lowest of the table, the last two were equivalents of using a system with context and without context, and it seems that the humans preferred the one without context slightly more in both translation directions than the one with context. So to conclude, we would say that SMT sometimes still works for tiny data, but more data helps the most. The larger batches help a lot, and using context needs some more work. Thank you for your attention.